In this video, we are studying about the transistor's configurations and its characteristics. As we know, there are three configurations in which a transistor is connected in a circuit. How we can considering the configurations? આમ જોવા જઈએ તો કેવી રીતે આપણે નક્કી કરીશું? The input and output circuit, which are the common terminal, because we know that the transistor is a three terminal. So base, collector and emitter. If any one the terminal are common between the input and output is called the common types configurations. So this way we are considering the common emitter configurations. In these configurations, the base is the input terminal and the collector is the output terminal. So as shown in the figure, VB is a connected is the input side and another source is a connected VC is the output side. But the emitter terminal is the common between the input and output. That's why it's called the common emitter. Now second way, the NPN common base mode. In these configurations, the emitter is the input and the collector is the output, but the base is the common terminal between the input and output. That's why it's called common base configurations. And last one is the common collector configurations, NPN mode, CC mode. In these configurations, the base is the input and emitter is the output terminal and collector is the common terminal between the input and output. So these are the three configurations of transistors. Most probably common emitter transistors configuration is used in applications. That's why we are only to study the characteristics of common emitter transistors in the next slide. Now characteristics of common emitter configurations. Now here the obtain the input and output characteristics, we draw the following common emitter practical circuit, because we want the readings of input sides and the output sides and draw the graph which are the possibilities or which are the functioning graph to operate the input side and the output side. Now as shown in the figure, here the common emitter transistor circuit is there. Only part of that the practically we are add the variable resistance and VBB and the VCC, the two source, and the 2 meters voltmeter and emitters at the input side, same way as the output side. Now is the base is the input terminal. At that time that we are connected emitter and the voltmeter VEB. Same way output side, the emitter is the measuring the current value of the IC and the voltmeter is the measuring the voltage of VC. Two are the variable resistance. We are adjust the value of input VBB and the VCC as shown in the figure. Now in common emitter mode, the IB and VB are the input variables. As shown in the figure, they are the input variable terminal. Output is the IC and VC. Now for the input characteristics, we are draw VI characteristics same as the diode, PN junction diode. The VEB is the input voltage and the IB is the input current. So these two are the variables and the different value of VC. So we change the value of VCC with the use of this variable rheostat at the output side. So VC is changed. So different value of VC, we observe the value of IB and VEB and plot the graph. So here is shown in the input characteristics graph. When output voltage is 0, it means the VCE is 0. Now the emitter base junction is forward bias. So characteristics same as the forward bias PN junction diode. And now VC is increased from the 0. It means the greater than 0. The width of the depletion regions at the collector base junction, it means the reverse side is the increase. So the base current is decrease compared to VC is equal to 0. So these are the input characteristics of common emitter transistors, which leads to less base current IB and increase the VB as shown in the graph. Now in the output characteristics, now the output we know the variable is the IC and VC. In that sections, the input side we are using the rheostat, variable rheostat. we value changed of IB. Now in the presence of IB is equal to 0, it means the no voltage is given to the input side. At the time we measure the value of IC and VC. At the time the value of IC and VC graph is given a one region, it's called CR, cutoff region. Now as increase the value of IB, then equivalent to value of IC is also increase. So this graph give us the three region: cutoff region, saturation region and active region. So we know that the active region, emitter base junction forward bias and collector base junction reverse bias. Cutoff region is the both junctions are the reverse bias, and saturation is the both junction is the forward bias. As shown in figure, the dark portions or shaded portion is called the saturation region, cutoff region. In between these regions, transistors always work very healthy. It's called the active region. Now next topic is the relations between the current gain alpha and the beta. Now gain is the same as the electrical terminology. Efficiency is the output by input. Here is the in electronics terms, the gain is the output by input. Same way the transistors can be find out in the terms of current, because the input current from emitter to collector or collector to emitter, we have to find out the value of the gain. A transistor is usually regarding as the current amplifier. Now is the fundamental formula, as we know, I is equal to IB plus IC. Now for to current amplification factor, we want to find the static current in a common base. Common base, it means the constant PCB. The alpha DC is equal to IC by IE. Same way when common emitter connection, here we are beta DC is equal to IC by IB at the constant value of VC. You should have to remember this value of IDC and beta DC, alpha DC and beta DC, IC by IE and IC by IB. So how we remember this value? Alpha DC. Alpha DC, it means IC by IE. Here are the C and E are used, IC and IE. B is not used, that's why it's the common base connection. And beta DC is IC by IB. Here C and B used and E is not used, that means common emitter. So for the easy to remember. Now is the relation between alpha DC and beta DC. Now we know that IC is equal to IB plus IC. So mathematical steps, dividing both sides by the IC. So IC divided, we get the 1 over alpha DC is equal to 1 over beta DC plus 1. So because the alpha DC value is put in this equation, so we get from the above equations or previous slide equations, we get the alpha DC and beta DC equation is alpha DC is equal to, in terms of beta DC, is the beta DC divided by 1 plus beta DC, and beta DC is equal to alpha DC divided by 1 minus alpha DC. So these are the main relations between the alpha, beta and beta. Okay, thank you.